Hello everyone, welcome to this tutorial. My name is Xarray. I'm a Google Earth Engine expert. In this tutorial, I'm gonna introduce one of the new remote sensing product releases by Awesome GEE Community Catalog dataset. As you can see, this product entitled Vegetation Optical Depth as an indicator shows the amount of water content stored in the vegetation canopy, operated by microwave wavelengths in shorter wavelengths and longer wavelengths. The shorter wavelengths with higher temporal frequency spanning from 1987 to 2021, and the longer wavelengths, the L band, covering 2010 and 2021 with 10 days temporal frequency. This product is very helpful for total water storage modeling or vegetation, water or moisture content estimation. So now in this tutorial I'm gonna show you how to plot or how to deal with this product in the Colab environment using Python API and XEE library. This tutorial is very helpful to get understanding about this product characteristic and processing using Python tools available in the Colab environment. Okay. Now in the first step, go to the Colab environment and make a new notebook. It's very easy to do and only needs one Gmail account connected to your Colab environment. Make a new notebook and then start coding without any challenge. So in the first step, we need to call Google Earth Engine related libraries. Start with EE and GEE map. These two libraries essential to make a connection between Colab and Earth Engine environment. The next one is Xarray. So import Xarray as XR. The Xarray is another library allowing us to convert the image collection to the array structure. So the Xarray and XEE together offer this capability where we can apply a wide range of machine learning algorithm already provided by the Python language. Okay, in the next step, we need to install the XEE. This is a revolutionary library already developed by the Google developers, allowing us to implement Xarray and Earth Engine together. That is very beneficial, and couple of tutorials I already shared on my YouTube channel addressing the application of the XEE in wide range of applications. So now I'm gonna install the XEE because it's not already available in the Colab environment. Pip install XEE, then import it into the code. After a few moments, the XEE installed completely, and when you saw successfully installed, then you can go to the next step. All the essential libraries collected. Next step is making a bridge between Earth Engine and Colab environment. Earth Engine, authenticate first, and then Earth Engine, initialize account information. The project name should be equal to your account cloud project name. If you don't know how to find it, just go to the code editor environment. In the upper right, there is a button here that shows the account information. Go to project info and find the cloud project and copy and paste it. Just like this. Very easy to do without any challenge. The next argument, OPTURL, already actually highlighted in the XEE instruction page on GitHub. Through this address, you can find detailed description and instruction about the XEE library. As you can see, the OPT URL already mentioned there. Just copy and paste like this. Now Colab asking you permission to connect to your Earth Engine account. By selecting account, the permission granted. Click on continue, and from now on you can bring Earth Engine functions into Colab environment for the dealing with satellite data analysis. In the first step, I'm gonna select the region of the interest, but in this tutorial I'm gonna to use basin layer to select the region of interest instead of drawing a simple rectangle. So to find the basin layers, go to the code editor environment and type hydroshed basin, just like this. Hydroshed basin, for example, scale 2. Wide range of scales or different range of scales are available. Smaller values, actually bigger basins, and vice versa. For example, here we have hydroshed basin level 2. So if you want to have a preview, it's very simple. Just type map.add layer for the whole of the world to see how different areas covered by the shapefile. So as you can see, very big basin borders actually available here, and you can find your own region of interest very easily. For example, I'm gonna select this basin. This is an example, and you can use this tutorial for your own region of interest, or you can apply this tutorial for different shapefile layers. Not only and don't limit yourself to what I'm mentioning in this tutorial. Maybe you have a different shapefile suggesting to try with your own, and just these are some tutorial content that addressing the capabilities behind the Earth Engine and the Colab environment. You must use these capabilities to extend your skills. Okay, for example, I'm gonna select this area. First of all, I need to call hydroshed basins level 2 in my code. Just go to the data properties and copy the collection snippet here. So for example, here we have a feature equals to Earth Engine.feature collection. So we need to select a point and bound our feature collection to that point. For example, I'm gonna select a point from this area for this area. To do this, we need an interface to draw a point. So through the ge.map, we can make a map layer here, and then we want to visualize the interface using map. So focus on your region of interest. Through the drawing tools, pick a marker and select the basin. Select a point that overlapped with your target basin. Well, same as what I did here. Now we need to have this point as a variable in the code to bound the feature collection based on. So now a variable point equals to from the map, select the last drawing feature. Draw last feature, convert it into a geometry structure, then make a print to make sure everything is fine that is not here. That should be geometry, just like this. So now bound your feature layer or basin layer to the point through the filter points filter bounds to the point. There it is. Okay, now in the next step, convert it into a geometry again, geometry, and do the simplification. That simplify with 1000 degree. There it is. And in the next step, I'm gonna show you how to highlight or how to visualize the feature or selected basin in the Colab environment. This is not addressed before on my tutorials on my YouTube channel. So the map number 2, a new interface is needed here. From gee.map here, a new map created. Then from in the map number 2, I'm gonna have focus to the feature with, for example, a scale size. For example, the scale size is number 10 or number 5, for example. So, and then I'm gonna actually plot the feature on map number 2. So that add layer, feature, leave the visualization empty, and the layer name is the basin. Map number 2, run this plot. After a few moments, you will have a new interface that shows your region of interest that is already simplified. There it is. Now I'm gonna call the satellite data product Vegetation Optical depths. So make a new code cell, a new variable, collection equals to, as you can see, two dataset available. One of them focused on shorter microwave wavelengths, and another one belongs to longer microwave wavelengths. The longer wavelengths penetrate more through the vegetation cover and offer a more accurate estimation about the inside moisture or the moisture content or the water content in the vegetation cover. That's why I prefer to use the L band for this tutorial. For example, bands C, X, K, and U, all of them give us a surface estimation about the moisture content, but the L band can penetrate more and give us estimation from moisture content that really is in the content because of the higher penetration. This dataset available with 10 days interval ranges from 2010 to 2021. If you are using this tutorial, if you are using this data product in your own study area, in your own investigation, it is necessary to address or cite this dataset through the instruction available here. So the collection equals to, as you can see, shorter wavelengths and longer wavelengths, two different variables. I'm gonna work with the shorter wavelengths, and the way of processing is the same for every one of them. So for example, the L band selected here, just copy the L band just like this, copy and paste this. Okay, this is the image collection. Now filter it based on a period of time, for example from 2015 to 2010, for example. And the next one is no need to filtering to a region of bounding to the region of interest, because this is not this frame actually doesn't have this kind of product, doesn't have framing structure same as Landsat and Sentinel, so the bounding the satellite images is not necessary, because in the further step I will show you how to bound your data to the region of interest without clipping and etc. So that filter date, and it has only one band, that's enough. And make a print from the image collection. So as you can see, something's wrong here. Maybe we can actually collection.size to see how many images available through the .get info. So the empty ranges, something's wrong. Empty date ranges and not supported. Let me to remove this part. Yeah, it's something's wrong because the end date is smaller than start date 2015 to 2020, and now you can see 180 images available. Let's try again. Here it is, one image collection with 180 features available, only one band, vegetation optical depths, and image or data properties available here, and shows which sensors utilized for these estimations, SMOS and SMAP satellites utilized, and here you can get more information through the properties available here. Okay, everything is fine. In the next step, we want to convert the image collection into Xarray structure. This is the step that XEE allowing us to do this conversion with combination of Xarray structure. A new variable dataset created equals to from XR or Xarray dataset, call your own dataset, that is collection, and the engine sets to Earth engine, just like this. Scale equals to 0.25. If you check the data characteristic here, mentioned 25 kilometer or 0.25 degree is the target resolution for this product. So and the CRS sets to EPSG 4326. This is a unique value we use to address WGS84 for all around the world. The next is the geometry area, the geometry location. This is the step that we can bound our data to a particular region already highlighted as a feature or basin. Yeah, the variable name is feature, just like this, and let's run. Now we are waiting that until conversion is done, then we can check the dataset contents. So the dataset including a multi-dimensional structure, one single dimension per time, longitude and latitude, and one variable that shows the vegetation optical depths. The higher value shows the higher moisture content and vice versa. Okay, in the next step, I'm gonna show you how to do the visualization and how to get export from this product for your own region of interest. Imagine I'm gonna convert it to an annual variation. So this a new variable as annual created, sets to get the data set, do the resample, time dimension equals to yearly, and then we want to get the average for each year, just like this. Let's run and then make a print of annual variable to make sure everything is fine. So as you can see, the time including 2015 to 2019, 5 images, 1 per each. So the variable name VOD, do the visualization like this. Dot plot, x axis sets to longitude, y axis latitude, and call axis time, and the next is robust, sets to true to avoid missing values impact on visualization. Let's run, and here you can see we have an annual variation of vegetation optical depth values that shows moisture content variation over the selected region of interest. You can also change the pattern of plot in the layout, like call wrap sets to 3, and let's run. As you can see here, we have a better view, and now you can see the variations for the region of interest. In the next step, I'm gonna show you how to plot the monthly variation. For example, imagine we want to have the average of vegetation optical depths for January, February until December through the whole period of time. So another variable, months created. The input dataset must grouped by temporal dimension, time, but filter them based on months and then calculate the average through the time. The monthly image is creating. You should wait for a couple of seconds. The waiting time depends on volume and volume of data, the size of your region, and the other things such as the pixel size. But hopefully processing quickly done in this step. The month image created only 12 months as expected, showing the average VOD for each one. So the months.select VOD.plot X sets to lon, Y sets to lat, call sets to months here because the temporal variation explaining by the month variable. Call wrap sets to number 4 and robust sets to true. Let's run a code. After a few moments, you can see the monthly variation for the region of interest. If you want to get output from the layout, first you must call import matplotlib.pyplot as plt. This is a main library that you can use for the plotting option, matplotlib. And now let's save the figure using the plt. So for example here, vod.png format dpi 360, and the next parameter is, let's say, bb box inches set to tight to include all elements into final layout. Let's run again. After a few moments, you can see the VOD PNG available in the left panel. Click on download, set an address, and check the output easily. So VOD image created with high quality, and you can use it in your own project or report. So as you can see, this is created. If you zoom in, you will find a good quality for the output. Okay, in the next step, imagine we have a point on this area and we want to monitor the variation of vegetation moisture content for that point with 10 days frequency over the time span. Go to the code editor environment and select a point. For example, I'm picking a point here and the location address highlighted here. So we can make a subset from the dataset. So dataset subset equals to, from the dataset, select a location through the latitude and longitude dimension, and the method sets to nearest because this is a point and we want to find the nearest value to the point. This is the longitude, the first value, and the next one is latitude, ds sub. There it is. And now, as you can see, only one value belongs to longitude and latitude. So let's do the plot. ds sub dot plot. You can see something's wrong. Variable is missed here. VOD. Let's run again. And here you can see the variation of vegetation optical depths through the selected time. So in this tutorial, you actually understand how to deal with this product. Now, if you want to save this product as a particular dataset in your own system, first you must install netcdf number 4 version. Then import netcdf4. Let's run. So the annual dataset, for example, I'm gonna get export from the annual dataset. So the annual dataset name was the annual, I think. Yes, this is the monthly, and this one is the annual. So the annual dot to netcdf. There it is. The variable name is the annual.nc. Let's run. After a few moments, the annual dataset with netcdf format is available, and you can download and save it on your own system. I hope you liked this tutorial as much as I did. You can find the code example below this video on my YouTube channel. If you had any problem in the code, feel free to compare my code with yours. If problem still exists, reach me out on the comment part on my YouTube channel. I will try to answer your questions as soon as possible. Please share these tutorials with all remote sensing fans in all around the world.